So we were looking at ray paths in an inhomogeneous medium, and we considered the inhomogeneous medium to be made up of several slices with varying refractive index n1, n2, n3, n4, so on and so forth. And if I consider a ray of light that is going from n1 at an angle theta 1, and say it is incident at an angle phi 1, right, and refracting it is refracting, and we call this angle of refraction as phi 2 and this angle as theta 2. And basically the same thing here too, right, that you could have this thing go this way, and so here you would have phi 3 and this is theta 3, right? And from Snell's law we have seen that basically n1 cosine theta 1 is equal to n2 cosine theta 2 n3 cosine theta 3. We derived how this came about in the first part. So if you have missed that, please go back and look through it again. So in general, you can write, if you have an index of refraction that is changing, we can write instead of n1, n2, n3, we can denote refractive index in general as a continuously varying quantity n of x, and even theta as a as a continuously changing variable, and we can write that as cosine theta of x. And all of these are equal to a constant, so we call that constant as, say, beta. So how do we determine this constant? If I know for most often a ray of light is coming from, say, air into some material or some lens or some object, right? So you would know the angle theta 1 at which this ray is emanating, and you can know what is the refractive index of the first layer, right? Say air, for example, right? Then you can calculate n1 cosine theta 1 experimentally, because you know where you are and where the object is, you know the refractive index right at the place of object, and if you take one ray of light going from the object at a particular angle like theta 1, right, we can calculate n1 cosine theta 1, and because all of these products of n and cosine theta are equal to the same constant, we can use this constant as beta. So we can write a general equation to define ray paths in a inhomogeneous medium as n of x cosine theta, x is equal to constant. Now, if you have ever closely observed the sunset or sunrise, you would see as if the sun appears, squished. The sun doesn't appear completely circular. Sometimes during the sunrise or the sunset, the sun looks elliptical or like an oval. So the reason is, this is, let's say we are here on Earth, right? Say the sun is far away here, right? So there is atmosphere around Earth, right? So there is, you have atmosphere here. So this is Earth, and this is Earth's atmosphere. So when sun rays are coming, right, when they enter the atmosphere, they bend, right? So you may see them bend like this, for example. So when you're viewing from Earth, you see these bent rays, and you see as if the sun is here, and the sun appears as if it is elliptical. That is because the medium in the atmosphere here is inhomogeneous, and so you would apply this n cosine theta is equal to constant. So you know the angle at which you are entering here, right? And you can see that the sun's image, because of the inhomogeneous refractive index, the sun's shape and the position change. You are not actually looking at the actual position of the sun, but you are looking at an apparent position, and the shape would also look very different. Now let's look at the same example in a different light. Um, so now here, when sun's rays are coming from very far away, you can consider them as parallel rays, for example. So they would be entering this. Let's say some rays are entering here horizontally, right? Some rays are entering here, let's say horizontally. Then once they enter the inhomogeneous medium, they would get bent, right? So now, using our understanding of how ray paths bend in an inhomogeneous medium, we can do the other way around. That is, we can start with rays in an inhomogeneous medium that are starting off at an angle, right? And see what should be the angle theta 1, right? What should be the angle theta 1 akin to this angle theta 1, such that when these rays exit, they come out horizontal, right? So we are starting with light in an inhomogeneous medium, and we would like to see at what angle would be the rays come out horizontal. So let's do an example here, right? So for example, if I am standing at x, let's say some x is equal to 0, right? And I have an inhomogeneous medium, right? And let's say the inhomogeneous medium ends at say uh, at 20 centimeters, right? At x is equal to 28 centimeters. So I have this x is equal to 1 to x is equal to 20 as an inhomogeneous medium. So if you want to visualize it, you can visualize it like made up of different refractive indices, like how we have seen. So I would like to calculate, right, the angle at which this incident ray should leave at theta, so that it comes out horizontal here, right? So I want to figure out what should be the angle here, so that whatever path the light takes in this part of the region, it bends in such a way that I want it to come out horizontally like that, right? So now we know that in an inhomogeneous medium, n of x cosine theta of x is constant. We call that constant as beta. So here, if I know the refractive index at the exit here, right? Let's say this index is given to you. So let's say here the refractive index is 1.039. Okay, and let's say the refractive index here is 1. Okay, so then it becomes easy, because here n cosine theta, right? Let's call this n1 cosine theta 1 in this slice should be equal to, let's call this n final, the final slice, right? Should be equal to n final cosine theta final. I want light to be coming out horizontally here, so I want it to come out at 0 degrees, right? So this is cosine 0 degrees. Cosine 0 is 1, so this n final times cosine final is essentially just n final. If n1 is 8, then the index of refraction is 1, so I can write cosine theta 1 as n final, which is 1.039, right? Then theta 1 is going to be cosine inverse 1.039, so that is roughly equal to 13 degrees. So a ray of light that is leaving at 13 degrees from here, right, would bend in such a way that at the end of 20 centimeters it would come out parallelly, right? This is very important in making instruments. For example, if you want to have a parallel beam of light, or if you're looking to bend a beam a particular way, then you can design a graded index material where the refractive index is changing, where the refractive index is inhomogeneous, right? So now let's go ahead and generalize this even more. So if we looked at how we had different slices of refractive index, so n1, n2, n3, so on and so forth, and if the ray of light is going here from theta 1 and it is incident at phi 1, right? So if I consider just one tiny slice of this ray, right, in a medium, right, where it is bending, if I zoom in, right, so the refractive index is changing continuously, so the ray is bending like that. So let's call this as x plane and this as z plane, right? Then I can take a small portion of the ray path. This is the light ray that is bending as it is going through an inhomogeneous medium, because the refractive index is changing, the light is also bending. So I'm considering a very tiny arc in that light ray. So this I'm going to call as ds, right? So this would be dz and this would be dx, right? And we're going to call this as angle as theta, right? What we're trying to do is, what we have derived, this n of x cosine theta of x is equal to beta, a constant, right? We are building on top of that to derive a mathematical expression for this ray path, right? So if I say y is equal to mx, then the ray path is straight line. So if I have a continuously varying refractive index, I would like to know what would be that ray path, right? So here I have ds, dx and dz, right? So I can approximate and write ds square as dx square plus dz square, right, from Pythagoras theorem. So then I can write this as ds by dz square as dx by dz square plus 1, right? I just pulled out dz square, right? And then now if you look at the figure here, so then write what cosine theta is in this figure. Cosine theta is adjacent side dz divided by the hypotenuse, which is ds. So I can write then ds by dz as 1 over cosine theta, right? But we also know from what we have derived for inhomogeneous medium that n times cosine theta is equal to beta. So from here I can write then 1 over cosine theta as beta over n, or n over beta. So 1 over cosine theta is n over beta, right, where this n is changing continuously. So ds by dz then is equal to n over beta, right? So then ds by dz, I can write it as n of x divided by beta square, right, is equal to dx by dz square plus 1, right? So now what we can do is we can take this equation and we can integrate it, right, to get the ray path x of z. So I can write this as dx by dz whole square is equal to n of x by beta whole square minus 1, right? So I can integrate this equation by parts, and if I integrate this equation with respect to z, right, then I can obtain an equation for an equation to represent the curved path that the ray of light takes, right? So you can either integrate it, or you can use numerical softwares to approximate a solution, right? So you can also write the same equation in a slightly different fashion, right? So to do that, what we can do is we can differentiate this whole thing with respect to z again, right? And then if we do this whole differentiation with respect to z again on this equation, then we can write that as, if I differentiate this with respect to z again, then I would get 2 times dx by dz, right? And then I have to differentiate again with respect to z, so I'm writing d square x by dz square. So I'm differentiating both sides by dz. This is just to make the equation look more convenient. This equation is all well and good. There's nothing wrong with it. We're just making it look more beautiful. We're just, performing some mathematical manipulations to make it a little more beautiful. So if I differentiate the left hand side with respect to z, I get the factor 2. Dx by dz is what I'm differentiating, so dx by dz. If I differentiate that with with z again, I get a double derivative. And on this side, right, when I differentiate 1 with respect to z, I get 0. So I don't need to care about that. Now if I differentiate this with respect to z, right, be very careful here. 1 over beta square is constant, right? 1 over beta square is just a constant, and so what I am really differentiating is n square. So if I differentiate n square, then I would have to write dn square. I'm differentiating n square as such, dn square by dz, right? So I will write this exact same equation on the next slide, and we'll do some more manipulations on that. So we have 2 times dx by dz times d square x by dz square is equal to 1 over beta square d of n square by dz. This is what we had on the last slide. So I'm going to write this as 1 over beta square d of n square by dx times dx by dz, right? So then I can cancel this dx by dz and this dx by dz. Then I would get 2 times d square x by dz square is equal to 1 over beta square dn square by dx, right? Or I can put this 2 down here with beta, or I can write d square x by dz square is equal to 1 over 2 beta square dn square by dx. So one thing that I would like to pause here, and I would like for you to ruminate or dwell upon, is the following. We are seeing something physically. There is a physical reality. For example, mirage that you see, right, is a phenomena that is happening. You're observing reality that the atmosphere has some graded index, or there may be materials that have graded refractive index. So you are trying to study those inhomogeneous mediums, and you know, right, that if the medium refractive index is changing, then the light is going to bend. You know that from refraction, right? All that we are doing with this equation is we are expressing how that ray of light is bending in a medium where refractive index is changing. So if you recall, we considered the medium like this. This is z, this is x, and we considered this is n1, this is n2, this is n3, so on and so forth. So light is entering somewhere at an angle theta 1, right, and it is bending. So the refractive index is changing along x, the refractive index is changing along x, and then because of this refractive index you are able to give an equation x of z for the path of light. So x of z, how ray path is changing in this plane because of the change in refractive index. So this equation d square x by dz square is equal to 1 over 2 beta square dn square by dx can give you hints about, or can actually tell you how a particular ray path is bending in an inhomogeneous medium, right? So the refractive index is changing along x, and you are getting an equation equation for path of light. So for example, now let's say if you know that there is a medium where the refractive index is changing linearly, so I can write in a medium, right? So let's say I have a medium here. The refractive index right as soon as you enter is n0, right? And this is the x-axis. As you go up, the refractive index is changing n of x as n0 plus kx. It's changing linearly, right? So now if you want to figure out what kind of path a ray would take, we would just simply use the equation d square x by dz square is equal to 1 over 2 beta square d of n square divided by dx, right? So then we just need to plug in what this dn square of dx is, and then we can figure it out, right? So or we can write this um, out, right? So if I want to write n square, right? Then I can write n square as n0 plus kx square. So I can write it as n0 square plus k square x square plus 2n0 kx, right? So if I do dn square by dx, the first term is constant, so 0 plus I get 2kx square, right? Plus the next term is a constant, so I get 2n0k, right? So this is a constant, this is 0. The only term that depends upon x is this, right? So then we can write this as d square x by dz square is equal to 1 over 2 beta square 2kx square, right, plus 1 over 2 beta square 2 n naught k, right? Here these two can cancel out, right? So does this. So I would have d square x by dz square as 1 over k over beta square x square plus some constant n0k, right? So these three things are really constant, right? So you can make a change of x to something like x prime, where x prime is x plus n0 by k, right? If I write it that way, then I can write this equation as d square x prime. So here then if you do the math here, you would get d square x prime by dz square is equal to some new constant c times x prime square, where new constant c would be something like k over beta. It's an easy transformation to do, right? So you can just combine this k by beta squares, right? And then you can see how you get this equation, right? So once you have this equation, it's very easy to solve for x. This is a simple differential equation, right? And if you solve for x, the solutions of this would be something like e to the power c x prime or e to the power minus c x prime, right? And sorry, e to the power cz or e to the power minus cz. We're solving it with respect to z. So then I can write for this path where the refractive index is changing linearly, then I can write x of z by solving this differential equation as something like minus n0 by k plus some constant a times e to the power cz, where c is k by beta, plus some constant b times e to the power minus cz. So I have mathematically derived a path for what I'm observing physically, right? So now if you know the initial angle, right, initial angle theta 1, right, then you can determine beta, right, because beta is n times cosine theta, right? You can determine beta, and from there you can plug in the values and you can figure out what should be the path of light, right? Okay, so this essentially concludes our discussion on ray paths in inhomogeneous medium. So now that we have understood this, let me tell you about something interesting. So all of you know what a black hole is, right? A black hole is essentially, if you were to ask a layman what a black hole is, you would probably hear the answer that even if light enters a black hole, it doesn't come out, right? So if you think about it, it is not because the light is feeling the gravitational force that it is not coming out. It is a little more deeper than that. If you have a black hole, it is so massive that it is warping the space-time around it. It is bending the space itself, right? And the light is still traveling in a straight line, right? But the space itself is bent, so that straight line is also on that space. The space itself is warped, right? That's why it goes in but never comes out, right? Because the space itself is bent that way. So now think about black hole, right? So you can think of black hole as something where any light that enters doesn't come out, right? There is a way to go in, but no way to come out, right? Now the opposite of that is a white hole. You have seen that if I have an inhomogeneous medium, I can basically the ray paths bend, right? So if I have an inhomogeneous medium, right, then I can have a ray that bends. So for example, if I have an inhomogeneous medium like this and some ray is starting out here, it may bend like that, right? So now can we make light bend so that such that there is a region of space where no light enters at all? The refractive index around this part of this medium is such that the all the rays of light coming near it get bent so that no light actually ends up entering this part of the space. In black hole, light enters but doesn't come out, and you know that in an inhomogeneous medium the ray paths can bend, so you can create a small region in space where the light is bending in such a way that no light is actually entering this particular part of space. That's a white hole, right? There have been some experiments done using white holes in a simple laboratory setup, and the event horizon, the so-called event horizon that is at the edge, right? You can study the event horizon by creating microscopic white holes in, say, some material like silica, for example, right? We can do this in the lab. In my lab, we can use a femtosecond laser basically to create a microscopic white hole, for example. But they're really hard to study. Nevertheless, I just wanted to mention this to you. So with that, I think we'll stop here. So this ends our discussion on ray paths in inhomogeneous medium. I will also post some homework and example problems online and send you an email in Canvas. Thank you.